Constant pressure calorimetry. The one we were looking at before was constant volume. Here's constant pressure. So here the calorimeter is much simpler. We can do it using two nested styrofoam cups. Styrofoam cups are used for hot drinks because they insulate your hand from the hot coffee. And here we're going to use two cups nested inside of each other because it gives you better insulation. There's a cork lid up here that's loose fitting. It's not clamped down or anything, so that if pressure built up, it could just bump up and let the pressure out. So the pressure's going to stay the same. We've got a thermometer in here so we can monitor the temperature, and then we generally need to stir it in some way. So at constant pressure, we've got the heat of reaction is equal to Q at constant pressure, which is Q for the reaction. We can't measure or calculate that directly, but we know that Q reaction is equal to negative Q solution, because if this is exothermic, the energy released by the reaction goes into the calorimeter. These reactions are happening in aqueous solution, so there's a lot of water, and that's considered part of the calorimeter. So that absorbs the heat, and the temperature goes up, and we can measure that. Q for the solution inside the calorimeter is equal to mc delta T, the mass of the solution and the specific heat capacity of the solution and the change in temperature. So we measure the change in temperature and the mass directly, and we look up the specific heat capacity, and we can calculate how much heat was absorbed by the solution. The heat absorbed by the solution was the heat released by the reaction, which is equal to the heat of reaction. If we want heat of reaction per mole, then we divide by the number of moles that actually reacted in the experiment. So the addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to this reaction. When 50 milliliters of 0.1 molar silver nitrate is combined with 50 milliliters of 0.1 molar HCl in a coffee cup calorimeter, the temperature changes from 23.40 degrees Celsius to 24.21 degrees Celsius. Calculate the heat of reaction for the reaction as written. Use 1 gram per milliliter as the density of the solution, and C equals 4.18 joules per gram degrees Celsius as the specific heat capacity. So we have a chemical reaction occurring in a coffee cup calorimeter. So we know that Q for the reaction is equal to negative Q for the solution. Whatever Q for the solution is, we just change the sign, and that equals Q reaction, which under these circumstances equals delta H for the reaction. Well, what's Q solution? Q solution is mc delta T. Did they give us the mass of the solution? No. What did they give us? They gave us volumes, right? If you put 50 milliliters of this and 50 milliliters of that together, what do you get? 100 milliliters, right? And we've got a density here. So I'll maybe stick this up at the top. So we've got 50 plus 50 milliliters. And we can use the density to convert that to grams. Milliliters cancel out. And so that's telling us we have 100.0 grams, the mass of the solution. So the mass is 100 grams. The specific heat capacity, they said use this. Okay. 4.18 joules over gram degrees Celsius. And then we need the change in temperature. Final minus initial. So delta T equals the final minus the initial. Delta T can be negative, and when it is, we need the negative sign. 24.21 minus 23.40. .81 degrees Celsius. So that's my change in temperature, 0.81 degrees Celsius. Let's check the units. Degrees Celsius cancel. Oops. And grams cancel. So we'll do the math here. 0.81 times 4.18 times 100, 338.58. And that's joules. So that is the amount of energy released, because this was absorbed by the solution, so that's the amount of energy released by the reaction. So Q reaction equals negative 338.58 joules. So we're almost there, but it wants delta H for the reaction as written. So we want to be able to say delta H equals, sloppy, and have this relate to the molar amounts in that equation. Is this the amount of energy that's released when 1 mole of silver nitrate reacts?
Yes.
Did we have a mole? How many moles of silver nitrate did we have? Well, this is the solution. 50 milliliters of 0.1 molar. So 50 milliliters is 0.05 liters, and 0.1 moles per liter is what molar means. Moles over liters. Do we have 1 mole of silver nitrate? No, not even close, right? We've got 0.005 moles, right? Did I do that math right? It's always dangerous when I do math in my head. So this is the amount of energy for 0.005 moles of silver nitrate. Did we have enough HCl to react with that many moles of silver nitrate? Well, look, we have the same volume and the same concentration of the HCl. So then we have the same number of moles. So we had just the right number of moles of each of them. I'm running out of room. So we've got negative 338.58 joules for every 0.00500 moles that reacts. And so our unit would have a fraction in here. Or maybe this would be better. Let's think of it this way. I want to know the amount of energy when 1 mole reacts, because that's what's listed in the equation. So I want to start with 1 mole of silver nitrate. And this is how much energy is released for every 0.005 moles. So I take my 338.58 and divide by 0.005. And I get 67716. Joules. So you can take the number of moles in the equation and use Q divided by the actual number of moles that reacted as a conversion factor to find the amount of energy that would be released for this many moles. Now that's a really big number, so we would tend to put that into kilo. See, I did 1, 2, 3, yeah. Kilojoules, so minus 68 kilojoules. And that's for 1 mole of this, or 1 mole of that, or 1 mole, or 1 mole. It's a lot of energy. Huh? Any questions? Yes?
It's asking for the Q in the reaction. Most likely it's
The unit, whether you put joules or kilojoules, really depends on the size of the number. So this, 67,000, that's a really big number. Yeah, and because of the number, the change in temperature, we were only going to have 2 sig figs, and so 68,000 joules, might as well make that into kilojoules. If it was really small, we wouldn't want to say 0.002 kilojoules. It'd be better to say it in joules then. If it doesn't specify kilojoules or joules, then either one is okay. Other questions?